What if 95% of the universe is completely invisible to you? You are like a fish that has no concept of the water it swims in, unaware of the vast, hidden reality that surrounds you. This is not science fiction, but the startling truth driving one of science's greatest quests, the mission of mapping the invisible. We will journey from the mind-bending edges of theoretical physics to the technologies that let us visualize the unseen, uncovering the secrets of dark matter, hidden dimensions, and the fabric of space-time itself. By the end, you will grasp a radical new picture of what the cosmos is truly made of. How can we map a world we cannot see? And what will these hidden maps reveal about our own place in reality? This invisible realm is far more than just things that are too small or distant for our eyes. It represents entire categories of existence that fundamentally do not interact with the very forces our perception relies on, light and electromagnetism. Think of your senses as a radio tuned to one specific station, completely missing the symphony of other signals broadcasting all around you. This is the nature of dark matter. We know it is there because we can watch its powerful gravitational pull guiding the motion of galaxies, yet it remains utterly transparent, a ghostly presence that light passes straight through. Then there is dark energy, an even more mysterious force that does not pull things together but pushes the very fabric of the cosmos apart, driving the accelerated expansion of the universe. You can think of it like the wind. You cannot see the air itself moving, but you see the leaves dancing and feel the pressure on your skin. In the same way, scientists observe the invisible by studying its profound effects on the visible world, watching how galaxies are shaped and spun by unseen hands. This foundational shift in understanding, from searching for dim objects to mapping forces that leave no light signature at all, forces us to ask a deeper question. What kind of map do you need when the territory itself is made of something you cannot touch or see? The answer lies in the mind-bending theoretical frameworks that attempt to describe this hidden reality. To map this invisible world, science must venture beyond the limits of our senses into the abstract realm of theoretical physics. A leading candidate for this ultimate map is string theory, a framework that proposes a radical reimagining of reality's building blocks. It suggests the universe is not made of zero-dimensional points, but of unimaginably tiny, vibrating strings. The different ways these strings vibrate are what create every particle and force we know, from the quarks in an atom to the photons carrying light. This elegant idea, however, comes with a profound requirement, one that demands we rewrite our understanding of space itself. For the math of string theory to work, the universe must have more than the three spatial dimensions of length, width, and height that we move through every day. It requires extra dimensions, perhaps 6 or 7 more, all curled up into a geometry so small it is hidden from our perception. Think of a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but up close you see its two-dimensional surface, a tube with a circular cross-section. In the same way, every point in our familiar three-dimensional space could harbor these extra, compactified dimensions, folded into intricate shapes known as Calabi-Yau manifolds. The specific geometry of these hidden shapes would dictate how the strings within them vibrate, which in turn would determine the very laws of physics for our visible universe. This theoretical leap paints a picture of a vast, hidden geometric landscape, a cosmic code underlying all of reality. Yet this is not the only powerful framework attempting to chart the invisible. But while string theory adds hidden dimensions to reality, another idea from the edge of physics does the exact opposite. it suggests that dimensions themselves might be an illusion. This is the holographic principle, a concept born from the fiery marriage of black hole physics and quantum gravity. It proposes that all the information describing everything within a volume of space, every star, every planet, every person, can be completely encoded on its outer boundary, like a cosmic barcode painted on a distant shell. The three-dimensional world we experience could be a kind of magnificent projection, a hologram generated from a vast, flat, two-dimensional surface. Think of a three-dimensional movie. The immersive world you see, with objects seeming to fly right at you, does not actually exist inside the screen. It is all projected from a flat, two-dimensional source. The holographic principle suggests our universe might operate in a similar, though far more profound, way. The solidity of your desk, the vastness of a galaxy, the very feeling of depth itself, could all be a projection from a fundamental layer of reality that is utterly flat. This shatters our most basic assumptions about locality, the idea that objects exist in specific, separate points in space. If true, two distant particles could be intimately connected because, at the fundamental level, their information is stored right next to each other on that distant cosmic surface. This blurs the line between what is physically real and what is pure information, forcing us to ask if the universe is ultimately made of stuff or of data. And it is this very question of information as the bedrock of reality that brings us back to the tangible mysteries hiding in our own cosmic neighborhood. The ghostly presence of dark matter is not just a modern theory, but a mystery with roots nearly a century old. Our story begins in the 1930s with a brilliant and often contentious astronomer named Fritz Zwicky. He was studying the Coma Cluster, a vast collection of galaxies bound together by gravity. By measuring how fast these galaxies were orbiting the cluster's center, Zwicky made a shocking calculation. The individual galaxies were moving so incredibly fast that the gravity from all the visible stars and gas should not have been nearly enough to hold the cluster together. It should have flown apart long ago. Zwicky concluded there had to be something else there, a huge amount of unseen mass providing the extra gravitational glue. He called this missing stuff Dunkelmaterei, the German words for dark matter. For decades, many scientists dismissed his idea, but the evidence became undeniable in the 1970s thanks to the work of astronomer Vera Rubin. She meticulously mapped the rotation of spiral galaxies, expecting to find that stars on the outer edges, far from the bright galactic core, would orbit more slowly, just as Pluto moves more slowly around the Sun than Earth does. But that is not what she saw. The stars on the outskirts were orbiting just as fast as those near the center. The only possible explanation was that each galaxy was embedded within a massive, invisible sphere of matter, a halo of dark matter whose gravity was whipping the outer stars around. This dark matter does not behave like normal matter. It does not emit, absorb, or reflect any form of light. It is completely transparent, a cosmic phantom that light passes straight through. Its only known interaction with our world is through gravity and possibly through the weak nuclear force, one of the four fundamental forces of nature. So what could it possibly be made of? Physicists have proposed several leading candidates. One class is known as WIMP, an acronym for weakly interacting massive particles. These are hypothetical particles that are heavy by subatomic standards and, as their name suggests, interact only via gravity and the weak force. Another promising candidate is the action, a particle that is trillions of times lighter than an electron but could exist in such vast numbers that it accounts for the missing mass. The hunt for these particles is one of the most intense efforts in modern science. Deep underground, in mines shielded from cosmic rays, experiments wait for the incredibly rare moment a WIMP might bump into an atomic nucleus. In powerful particle colliders like the Large Hadron Collider, scientists are trying to create dark matter particles by smashing ordinary particles together at nearly the speed of light. Finding dark matter is not just about solving a cosmic puzzle. It is the key to understanding why the universe looks the way it does. The gravitational pull of dark matter acted as a cosmic scaffold, a hidden framework upon which ordinary matter could clump together to form the very first galaxies and the vast, web-like structure of the cosmos we see today. Without this invisible architecture, stars and planets might never have formed at all. But if dark matter is the hidden skeleton of the cosmos, then what is the strange force that seems to be tearing its very fabric apart? The discovery of dark matter reshaped our understanding of the cosmos, but it was the revelation of a second, even stranger component that truly turned cosmology on its head. This is the mystery of dark energy. While dark matter's gravity pulls the universe together, dark energy does the exact opposite. It pushes the entire cosmos apart, and it makes up a staggering 68% of everything. For most of the 20th century, scientists believed the universe's expansion, following the Big Bang, should be gradually slowing down due to the collective gravitational pull of all the matter within it. The great question was whether that slowdown would be enough for gravity to eventually win, pulling everything back in a big crunch, or if the universe would keep expanding forever, just at an ever-decreasing rate. Then, in the late 1990s, two independent teams of astronomers made a landmark discovery by observing a specific kind of stellar explosion in incredibly distant galaxies, a Type I, a supernova. These explosions are what scientists call standard candles, meaning their intrinsic brightness is known. By measuring how dim they appear from Earth, astronomers can calculate their precise distance. They can also measure how much the light from these explosions has been stretched, or red-shifted, by the expansion of the universe. The teams expected to see that the most distant supernova, whose light had been traveling for billions of years, would show signs of a universe expanding faster in the past, confirming the expected slowdown. Instead, they found the opposite. The distant explosions were fainter than they should have been, meaning the universe is not slowing down at all. It is accelerating. The expansion rate is getting faster and faster over time, as if some mysterious repulsive force is stretching the very fabric of space-time itself. This was the signature of dark energy. The leading theoretical model for this bizarre force is something Einstein actually conceived of and then later discarded: the cosmological constant. This idea represents a constant energy density that is an inherent property of the vacuum of space itself. Think of empty space not as truly empty, but as a seething foam of virtual particles that constantly flicker in and out of existence. According to quantum physics, this vacuum should possess a certain energy. The cosmological constant treats this energy as a fixed property of space, so that as the universe expands and more space comes into existence, the total amount of this repulsive energy increases, driving the acceleration ever faster. However, there is a colossal problem. When physicists calculate how much energy this quantum foam should have, the theoretical value is a number so astronomically huge, one followed by 120 zeros, that it should have ripped the universe apart in its first instant of existence. The observed value of the cosmological constant is this same enormous number divided by another number with over 120 zeros, a discrepancy so vast it is considered the worst theoretical prediction in the entire history of physics. This forces us to confront a profound question. Is dark energy a simple, unchanging property of empty space, or is it something dynamic, a field that could evolve or decay over billions of years? The answer dictates the ultimate fate of everything. A constant dark energy leads to a cold, lonely, and endless expansion, while a dynamic one could lead to a future far more strange or violent. And the key to that answer, the very shape of this fate, is written in the geometry of the cosmos itself. The ultimate fate of the cosmos is written in its geometry. To understand our universe's shape, we must ask a deceptively simple question. What happens to parallel lines as they travel across the cosmos? Do they stay perfectly parallel? Do they slowly converge, or do they drift apart? The answer depends on the total density of all the stuff in the universe, both the visible and the invisible, the matter and the dark energy. This density warps the fabric of space-time on the grandest scale imaginable, creating one of three possible geometries. Think of drawing a giant triangle between three galaxies. On a flat surface, the angles of any triangle always add up to 180 degrees. This is the geometry we learn in school, but draw that same triangle on the surface of a sphere like the Earth. Start at the North Pole, travel down to the equator, go a quarter of the way around the globe, and then head back to the North Pole. You have just drawn a triangle with three right angles adding up to 270 degrees. This is positive curvature. Now imagine a surface with a saddle shape, curving upwards in one direction and downwards in the other. On this hyperbolic surface, the angles of a triangle would add up to less than 180 degrees. This is negative curvature. For decades, cosmologists have been trying to measure which of these shapes describes our entire universe. The tool they use is the oldest light in existence, the cosmic microwave background. This faint afterglow from the Big Bang is a snapshot of the infant universe, and it is covered in tiny hot and cold spots, like a fossilized imprint of the earliest density fluctuations. Missions like the Planck Space Observatory have mapped these spots with incredible precision. The size and pattern of these spots act as a cosmic ruler. If the universe were positively curved like a sphere, the spots would appear larger. If it were negatively curved like a saddle, they would appear smaller. The Planck data revealed with stunning certainty that the spots match the pattern expected for a perfectly flat universe. The angles of the cosmic triangle add up to exactly 180 degrees. A flat geometry has staggering implications. It suggests the universe is most likely infinite, stretching on forever in every direction. It also provides powerful support for the theory of cosmic inflation, the idea that the universe underwent a period of unimaginably rapid expansion in its first fleeting moments, smoothing it out into the flat geometry we observe today. This vast, flat canvas is not empty. It is the stage upon which the invisible architecture of dark matter operates. The gravitational pull of this unseen substance sculpted those tiny fluctuations in the early universe into the magnificent cosmic web we see today, a sprawling network of galaxies and vast, empty voids. We have mapped the geometry of the stage itself, but how do we begin to see the invisible scaffold that built the structures upon it? This cosmic scaffold, the dark matter web, is one of the most magnificent structures in existence. It is a vast, interconnected network, a cosmic sponge on the grandest possible scale. Imagine looking out at the night sky and seeing not just scattered stars, but the underlying architecture of reality itself. Gigantic filaments of dark matter stretch across billions of light years, connecting dense nodes where thousands of galaxies swarm together in massive clusters. Between these threads lie the voids, unimaginably vast and nearly empty regions of space that make up most of the universe's volume. The galaxies we see with our telescopes are merely the visible tracers, the glittering lights strung along this invisible framework. They outline a structure they did not build, following the gravitational blueprint of the dark matter. So how can we possibly map this ghostly skeleton if we cannot see it directly? The answer lies not in telescopes, but in the raw computational power of supercomputers. Scientists create virtual universes inside these machines, starting with the near-uniform soup of particles just after the Big Bang. They program in all the known laws of physics, especially gravity, and then set the simulation in motion, watching as billions of years pass in a matter of weeks. One of the most famous of these, the Millennium simulation, used more than 10 billion particles to represent dark matter, tracing how its own gravity would cause it to clump and weave itself into a cosmic web over cosmic time. The result is a breathtaking visualization, a swirling, evolving map of dark matter distribution. These are not photographs but data-driven predictions. They show us what the invisible scaffolding of the cosmos must look like based on everything we know. It is a theoretical map of a hidden world, but a map is only as good as its correspondence to the real territory. The stunning success of these simulations in reproducing the large-scale structure we observe gives us tremendous confidence that we are on the right track. Yet it also pushes us to find tangible, observational proof. How do we gather real data to confirm that this simulated web is truly out there, woven through the darkness between the stars? Einstein gave us the key to seeing the invisible. He predicted that massive objects do not simply sit in space, they warp the very fabric of space-time around them. And since light travels along this fabric, its path bends around these cosmic weights, just as a marble would roll along a curved indentation on a stretched sheet. This phenomenon, gravitational lensing, transforms the universe into a colossal telescope, using gravity itself as its lens. The most dramatic form is strong lensing. When a massive object like a galaxy cluster sits directly between us and a distant galaxy, it can act like a giant magnifying glass, warping the background light into spectacular arcs, rings, and even multiple images of the same galaxy. It is a perfect, natural demonstration of distorted spacetime, but to map the subtle, web-like distribution of dark matter, scientists rely on a far more pervasive and delicate effect: weak gravitational lensing. Across the cosmos, the light from billions of faint, distant galaxies travels through the foreground cosmic web, the vast filaments and halos of dark matter. This invisible scaffolding imparts a tiny, coherent distortion to the shapes of these background galaxies, stretching them ever so slightly in a radial pattern around the unseen mass. No single distortion is obvious, it is a statistical signal. By meticulously measuring the shapes and alignments of millions of galaxies across a huge patch of sky, astronomers can detect this collective shearing effect. Projects like the Dark Energy Survey perform this painstaking work, creating detailed mass maps of the sky. These maps reveal the true distribution of all matter, visible and dark, painting a picture of the cosmic skeleton in exquisite detail. A third type, microlensing, works on a smaller scale. It occurs when a compact object like a solitary star, a planet, or even a black hole passes in front of a more distant star. The foreground object's gravity briefly acts as a tiny lens, amplifying the background star's light in a distinct, telltale spike of brightness. This technique has been incredibly successful in finding rogue planets, worlds drifting alone in the dark between stars. From the grandest cosmic filaments to the smallest isolated objects, gravitational lensing allows us to trace the unseen by watching how it sculpts the light of the scene. It is a direct observation of gravity's architecture, a way to watch spacetime itself curve under the weight of the invisible. This ability to see with gravity rather than light opens a window to phenomena that are completely dark, a capability that is about to be supercharged by our next great leap in observation. Deep underground, in the profound silence of an old gold mine in South Dakota, a different kind of astronomer is at work. They are not looking at the sky, but waiting for a ghost to bump into a crystal-clear tank of liquid xenon. This is the LUX-ZEPLIN Experiment, one of the most sensitive dark matter detectors ever built. Its location, a mile beneath the surface, is not an accident. The solid rock overhead acts as a colossal shield, blocking out the constant rain of cosmic rays and other particles that would completely overwhelm the delicate signal the scientists are hunting for. Inside its cryogenic vessel, they are waiting for the unimaginably rare event, the moment a WIMP, a weakly interacting massive particle, the leading dark matter candidate, finally collides with the nucleus of a xenon atom. Think of it as trying to hear a single, specific pin drop in a city during a thunderstorm. First, you must build a room so quiet that no outside sound can get in. Then, you must develop a microphone so sensitive it can pick up that one tiny vibration, and be smart enough to ignore all the other tiny sounds, like the scuttling of a dust mite or the creaking of the floorboards. That is the monumental challenge of direct detection. When a collision happens, it produces two distinct signals, a tiny flash of light and a puff of electrical charge. By precisely measuring the timing and ratio of these two signals, the detectors can, in theory, distinguish a potential dark matter interaction from the relentless background noise of mundane radioactive decays. So far, these collisions have remained elusive, with no definitive signal yet recorded. But every null result is not a failure. It is a mapmaker drawing a line through a territory where the monster does not live, narrowing the search. The hunt also extends far beyond these deep underground laboratories. In space, telescopes are scanning the skies for indirect evidence of dark matter's presence. The theory suggests that when two dark matter particles meet, they could annihilate each other, transforming into a shower of familiar particles like gamma rays, the most energetic form of light. Scientists meticulously scan the center of our galaxy, or nearby dwarf galaxies that are rich in dark matter, searching for an unexplained excess of these gamma rays that cannot be accounted for by any known astrophysical process. It is a search for the ghostly echo of an invisible collision, the faint signature of the universe's most abundant substance revealing itself through its own destruction. These parallel quests, one waiting in profound stillness and the other scanning the heavens for explosive clues, represent the cutting edge of the particle hunt. They are our best attempts to reach out and finally touch the invisible architecture of the cosmos. And as we push the limits of detection, we are simultaneously building machines that can see the universe not with light, but with the ripples in space-time itself. These hidden dimensions of string theory are not merely mathematical abstractions. Scientists are actively hunting for their physical footprints in the real world, designing ingenious experiments to catch a glimpse of a reality with more than three spatial directions. One of the most direct ways to search is by testing gravity itself. Isaac Newton and later Einstein described a force that weakens with the square of the distance. But what if that law is not the final word? Some models suggest that on extremely tiny scales, smaller than a millimeter, the gravitational force could begin to leak into these compact extra dimensions, causing a detectable deviation from the classic inverse square law. To test this, physicists use devices of breathtaking sensitivity called torsion balances. Imagine a bar suspended by an incredibly fine thread, with small weights attached to each end. This instrument is so delicate it can measure twists and rotations caused by forces far weaker than the gentle push of a single breath. researchers bring a dense attractor mass excruciatingly close to this balance, looking for any extra gravitational tug that would not fit the predictions of standard physics. It is like listening for a faint, new harmonic in a song you have heard your entire life, a subtle note that would reveal a hidden resonance with another realm. So far, gravity has behaved exactly as expected down to microscopic distances, but the search continues, each experiment ruling out another possible size and shape for these hidden dimensions. Meanwhile, at the other end of the scale, the world's most powerful machine, the Large Hadron Collider, is attempting to create evidence for extra dimensions. When it smashes protons together at nearly the speed of light, it concentrates an immense amount of energy into a vanishingly small point. One tantalizing possibility is that this energy could, for a fleeting instant, create a microscopic black hole, an object so dense its gravity would be overwhelming. In our standard three-dimensional world, the energies needed to make such a tiny black hole are astronomically beyond our reach. But if extra dimensions exist, they could effectively magnify gravity's strength on small scales, making the formation of these quantum black holes possible. The collider's detectors would see the spectacular signature of such an event, a burst of particles radiating from a point, followed by nothing, as the black hole evaporates almost instantly. Another signature would be missing energy, where the accounting of energy and momentum after a collision does not add up, suggesting that some particles or energy have literally traveled out of our dimensional plane into another. To date, no confirmed microscopic black holes or unexplained missing energy have been found, but the very act of looking is a profound testament to human curiosity. We are building machines that can probe the geometry of reality itself, testing the wildest theoretical ideas with rigorous, painstaking experiment. This relentless drive to map the invisible, from the quantum to the cosmic, shows that our understanding of the universe is not limited by our senses, but only by the questions we dare to ask. The equations scrawled across a blackboard are more than abstract symbols. They are the native language of the hidden cosmos, a precise vocabulary for describing realities our senses cannot grasp. Mathematics allows us to construct maps of the invisible, translating the warping of space-time and the whisper of extra dimensions into a form the human mind can explore. This is not about simple arithmetic. To chart these unseen realms, physicists wield tools of profound complexity, like tensor calculus and differential geometry. These disciplines deal with quantities and shapes that are not fixed, but that change and curve from every possible perspective. They provide the grammar needed to describe a universe where space itself is dynamic. The most famous example of this mathematical mapping is Einstein's field equations. In a breathtakingly compact form, they state a radical truth. The geometry of spacetime, its curves and warps, is not a static stage. It is a dynamic actor, and its shape is directly determined by the energy and matter within it. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. Those elegant symbols are a complete set of instructions for the gravitational force, a mathematical lens that lets us visualize the gravitational wells around planets, the twisting vortex around a spinning black hole, and the expansion of the entire cosmos. When we see an artist's impression of a black hole warping the starlight behind it, that vivid image was born from the cold, hard logic of these equations. The mathematics came first, painting a picture of bent light and an event horizon long before any telescope could hope to see one. This abstract mapping extends to the frontiers of particle physics and string theory. The properties of a hypothetical dark matter particle, or the possible vibrations of a string in a 10-dimensional reality, are all defined and explored through their mathematical descriptions. The symbols and operations are not merely calculations. They are the reality. They allow us to see with the mind's eye what our physical eyes are blind to, transforming the intangible into a landscape we can navigate and understand. This profound mental mapping, however, requires a bridge to our physical world, a way to transform abstract equations into tangible evidence that our instruments can detect. These digital universes are born from pure mathematics and raw computational power. Inside the world's most advanced supercomputers, cosmologists perform a kind of ultimate experiment, building a cosmos from scratch to see if their theories of the invisible hold up. They start with a near-perfectly smooth, expanding grid of space, populated by billions of virtual particles that represent the dark matter and normal matter present just after the Big Bang. This is the initial condition, the digital seed. Then they set the simulation in motion, governed by a complex code that embodies all the known laws of physics, especially the relentless pull of gravity. Over weeks of calculation, the computer fast-forwards through billions of years of cosmic evolution. The gravity from each particle tugs on every other particle, a computational problem of staggering complexity. Slowly, the uniform soup begins to clump. Tiny ripples of density grow under their own weight, first forming delicate filaments, then condensing into massive halos of dark matter. The ordinary matter, the gas, follows this invisible gravitational blueprint, flowing into the dark matter wells to form galaxies. Projects like the Illustris TNG simulation take this even further. They do not just track dark matter, they incorporate the messy, dynamic physics of the visible universe. Their code simulates the hydrodynamics of cosmic gas, the violent birth of stars within swirling nebulae, and the explosive feedback from supernova and supermassive black holes at the hearts of galaxies. These digital black holes can grow, devour material, and blast out enormous jets of energy, which in turn heat the surrounding gas and regulate the formation of new stars. The result is not just a map of mass, but a synthetic, dynamic sky. When you look at the output of Illustris TNG, you see a virtual universe that is eerily similar to our own, complete with realistic spiral and elliptical galaxies, vast clusters, and empty voids, all emerging naturally from the code. This digital laboratory is our testing ground. By comparing these simulated skies directly with deep field observations from the Hubble and James Webb Space Telescopes, scientists can perform a crucial reality check. Does the distribution of galaxies in the simulation match the real cosmos? Do the virtual galaxies have the right shapes, sizes, and populations of stars? When the simulation matches reality, it builds tremendous confidence that our underlying theories about dark matter and dark energy are correct. When it does not, it points directly to a flaw in our understanding, forcing us to go back and tweak the model to refine our map of the invisible. It is a continuous cycle of prediction, comparison, and revision, a conversation with a universe we built inside a machine. Our ears can now join our eyes in the cosmic search. Scientists are translating the universe's hidden data into sound, a process called data sonification. This technique takes the complex numerical outputs from telescopes and detectors and maps them into audio frequencies, amplitudes, and timbres that our brains can process. It is a new way of listening to the cosmos. One project transformed the subtle temperature fluctuations in the cosmic microwave background, that ancient afterglow of the Big Bang, into a haunting soundscape. The map of the infant universe, with its hot and cold spots, becomes a shimmering drone where regions of higher density sound at a higher pitch, creating an auditory imprint of the universe's very first structures. In another application, the light from distant stars is turned into music, as an exoplanet transits in front of its host star, causing a tiny, periodic dip in brightness. That light curve becomes a rhythmic pulse. Listeners can hear the precise orbital period of a world they will never see, a rhythmic beat against the steady tone of the star. The most dramatic sounds come from gravitational wave observatories. The signal from two black holes colliding, an event completely invisible in light, is rendered as the iconic chirp, a rapid rise in pitch and amplitude that marks the final, frantic spiraling of these massive objects before their merger. This is not just for public outreach. The human auditory system is exceptionally good at detecting subtle patterns and rhythmic anomalies. A researcher staring at a graph of squiggly lines might miss a faint, repeating irregularity, but their ear could immediately pick it up as an odd rhythm or an unexpected harmonic in the data's song. Sonification adds a new dimension to discovery, allowing us to perceive the invisible not as a static image, but as a dynamic, evolving symphony. It proves that the tools we build to explore reality are not just calculators, but extensions of our own senses, translating the silent language of the cosmos into a form we can feel. Our own biology creates the very first barrier to seeing the universe's hidden layers. We are exquisitely tuned to survive on the surface of this planet, our senses honed to detect the immediate threats and opportunities of a macroscopic world. We see the narrow band of light we call the visible spectrum, but this is a mere sliver of the vast electromagnetic tapestry. Beyond the reds and violets we perceive, there is an entire cosmos of information broadcasting all around us, from the long, gentle radio waves that carry our music to the incredibly energetic gamma rays born in stellar explosions. We are deaf to this symphony, surrounded by forces we cannot feel. We live our entire lives bathed in the planet's magnetic field, a force that guides migrating birds and shapes our atmosphere, yet we have no direct sensory organ to perceive its subtle pull. Our perspective is also shackled by scale. The frantic, probabilistic dance of the quantum world is too small for our senses to register, while the majestic, slow-motion choreography of galaxies is too vast for our brief lives to comprehend. Consider the mantis shrimp, a marine creature that perceives the world in a way we can only mathematically describe. Its eyes contain 16 different types of color receptors, allowing it to see a spectrum of colors, including polarized light patterns, that are completely invisible to our three-receptor vision. The shrimp inhabits a richer, more vibrant visual reality than we can ever naturally experience. This is not a failure of our design, but a definition of our starting point. Our inherent limitations are the very reason science exists, the driving force behind every telescope, every microscope, and every particle detector. They are not walls to imprison us, but the foundation from which we build all our tools to reach beyond the sensory prison of our own evolution. This relentless expansion of our cosmic maps forces a confrontation with one of philosophy's oldest puzzles. If the substance of the universe is 95% invisible, what can we truly claim is real? Our everyday experience tells us that the solid ground beneath our feet and the stars in the sky are the fundamental reality. Yet physics reveals these to be a mere shimmering surface on a deep, dark ocean of forces and substances we cannot naturally perceive. This tension sits at the heart of a long-standing debate about the very purpose of science. On one side is the stance of scientific realism. This philosophy argues that our most successful theories, from general relativity to the dark matter model, are more than just convenient math. They are accurate descriptions of a reality that exists completely independently of human minds or our instruments. The dark matter halo around our galaxy is really there, a vast, invisible structure whether or not any being is around to deduce its existence. Our maps are successful precisely because they correspond to the true, mind-independent territory. A starkly different view is known as instrumentalism. From this perspective, scientific theories are not literal descriptions of the world. They are incredibly powerful and useful tools for organizing our observations and making accurate predictions. Asking if dark energy is real is, for an instrumentalist, like asking if the number 5 is real. It is a concept within a model that works brilliantly to predict the accelerating expansion of the universe, and that is its entire value. The model is a tool, not a picture. So where does that leave us with something like a curled-up dimension from string theory? It is a concept that exists as a consistent mathematical possibility, essential for the equations to function. But if it is forever beyond any possible direct observation, can we call it real in the same way we call a rock real? Or does its reality exist only within the abstract, relational world of mathematics, a powerful narrative that helps our minds grasp a cosmos far stranger than we ever imagined? Perhaps our act of mapping the invisible is not a passive discovery, but an active act of creation within the human sphere. By visualizing the cosmic web through gravitational lensing, or by giving dark matter a name and a story, we are weaving these concepts into the fabric of our shared understanding. We are building a new reality, a cognitive landscape where the invisible gains substance and meaning. This does not make it less true, but it acknowledges that our reality is always a partnership between the world as it is and the minds we use to comprehend it. The quest to map the invisible is ultimately a quest to understand the nature of existence itself, pushing us to decide if reality is what we can touch or what we can comprehend. These artistic renderings are a necessary translation, a bridge between the abstract equations and our own human need to see. When a scientist describes the warped spacetime around a black hole, the concept remains locked in complex tensor calculus. But when a scientific illustrator collaborates with that researcher, the mathematics is reborn as a breathtaking visual, a swirling vortex of deep blues and fiery golds where the fabric of the cosmos is twisted into a cosmic whirlpool. This is not a photograph, it is an interpretive guide using color and form to convey forces we can never witness with a telescope. The intense gravitational lensing, depicted as a perfect ring of distorted starlight, makes the invisible curvature of space intuitively, viscerally understandable. Similarly, the intricate, multi-dimensional shapes of Calabi-Yau manifolds from string theory are brought to life through digital sculpture. Artists work from the mathematical definitions to model these six-dimensional objects, projecting them into our three-dimensional view. The result is a stunning, labyrinthine geometry, a crystalline-like structure that helps us grasp the hidden spatial order that might underpin all of physical reality. These visualizations are careful collaborations. The artist provides the visual vocabulary, while the scientist ensures the underlying physics remains accurate, that the way light bends or the way dimensions are folded aligns with the theory. The goal is not to create a literal snapshot, but to build a visual metaphor that is both scientifically informed and emotionally resonant. This fusion extends beyond still images into immersive experiences. Data-driven art installations can take the three-dimensional maps of the dark matter cosmic web, generated by supercomputer simulations, and transform them into vast, walk-through sculptures made of light and thread. Visitors can literally stand inside the invisible architecture of the universe, feeling the scale of the filaments and voids in a way a graph could never communicate. The choice of color is not arbitrary. Cool blues might represent regions of low density, while warm reds indicate the dense knots where dark matter halos reside. This use of a visual spectrum we understand instantly conveys relationships and dynamics that would take paragraphs to explain. This artistic partnership is more than just public communication. It is a form of thinking in its own right. By translating raw data into a visual or spatial form, artists can sometimes spot patterns or ask questions that a scientist, steeped in numbers, might overlook. The process of rendering the unseeable forces a different kind of engagement with the concept, offering a fresh perspective that can, on occasion, spark a new line of scientific inquiry. It completes a vital loop, transforming the cold data of the invisible world into a shared experience that connects directly to our human sense of wonder. These metaphors are the very tools that allow us to think about the unthinkable. When we describe a higher dimension as a garden hose, viewing its circular cross-section only upon close inspection, we are performing a brilliant act of cognitive translation. We are taking a concept that has no direct sensory counterpart and mapping it onto a structure our brains can manipulate. This is the immense power of analogy. It makes the profoundly strange feel momentarily familiar. The holographic principle analogy, comparing our universe to a three-dimensional movie projected from a flat screen, gives us a tangible handle on a concept that otherwise vaporizes upon contact with intuition. It provides a narrative, a how, for something that exists purely as a set of equations. These are not just teaching aids, they are essential stepping stones. Our minds evolved to navigate a world of three spatial dimensions, of solid objects and direct cause and effect. They are not wired to visualize a six-dimensional Calabi-Yau manifold or a 10-dimensional superstring. So we build bridges from the world we know to the world that is. Yet every bridge has a limit, and every analogy eventually breaks down. The garden hose helps us visualize a compactified dimension, but it fails to capture what the dimension itself is made of, or how it could influence the laws of physics. The hologram analogy brilliantly conveys the idea of information encoded on a surface, but it risks making us imagine a literal projector somewhere in space, a cosmic cinema that the principle does not require. The map is not the territory. These analogies are simplified, low-resolution pictures of a far more complex and alien reality. They are the training wheels for the mind, necessary for the first shaky ride toward comprehension, but they must be cast aside for the deeper, more abstract language of mathematics to take us the full distance. Their true value lies not in being perfectly accurate, but in being directionally correct. They point our intuition toward the right part of the problem, giving us a fighting chance to grasp the logic behind the symbols. They are the stories we tell ourselves to make the cosmos feel less lonely, a shared vocabulary of wonder that allows us to collectively inch closer to the invisible architecture of everything. Our ancestors would have seen a lodestone mysteriously tug on a piece of iron and attributed its power to spirits or gods. The force of magnetism was a real, tangible effect with no visible cause, a perfect example of an invisible reality that seemed magical before it became scientific. Gravity was no different. For centuries, the idea that the Earth could pull the moon across the vast emptiness of space without any physical connection was considered absurd by many. These forces were the original dark matters, influences that shaped the world in profound ways while remaining completely unseen. It was only through the language of mathematics and the rigor of experiment that these invisible actors were coaxed out of the shadows and transformed from mystical concepts into the well-understood fundamental forces we teach in classrooms today. This pattern of discovery repeats itself again with the very nature of matter. The idea of the atom was first proposed by ancient Greek philosophers as a pure thought experiment, a logical necessity for a universe that was not infinitely divisible. For over 2 millennia, it remained a philosophical speculation with no physical proof. Then, in the early 20th century, technology finally caught up with theory. Through painstaking experiments, scientists like Ernest Rutherford peered into the heart of matter, not with light, but by firing alpha particles at thin gold foil and watching how they scattered. The results revealed a shocking truth that atoms were mostly empty space with a tiny, incredibly dense nucleus at their center. The invisible building block was suddenly, tangibly real. This journey did not stop there. The nucleus itself was split, revealing a whole zoo of even more fundamental, even more invisible particles, quarks and leptons, the true bedrock of the visible world. Perhaps the most dramatic shift came from an invisible world not in the stars but in our own bodies. For most of human history, disease was a punishment from the gods or a consequence of bad air. The idea that our world was teeming with invisible living creatures, germs, that could invade and cause illness was met with scorn and ridicule. When doctors like Ignaz Semmelweis proposed that simply washing hands could prevent fatal childbed fever, he was ostracized by his own profession. It took the powerful visual proof of the microscope, showing these microorganisms swimming in a drop of water, to shatter the old paradigm and launch a medical revolution that has saved countless millions of lives. In every case, from force to particle to pathogen, the story is the same. A concept that begins as a heretical speculation, an invisible influence dismissed by the establishment, slowly gains credibility through indirect evidence. Then a new tool is invented, a new way of seeing that finally makes the invisible visible, and our understanding of reality is permanently and radically expanded. We are living in the middle of that exact same story today. Dark matter and hidden dimensions are our generation's germs and atoms, theoretical constructs that currently defy direct detection. The history of science is a long, triumphant record of proving that our senses are not the final arbiters of reality. Our current maps of the invisible may be drawn in the abstract ink of mathematics and simulated in supercomputers, but history gives us every reason to believe they are pointing toward a truth that future tools will one day bring into stunning focus. The next leap in our cosmic perception is already under construction. Across the globe and in the vacuum of space, a new generation of observatories is being built, designed not just to see farther, but to see differently. These instruments will act as extensions of our senses, calibrated specifically to trace the contours of the invisible universe in the high, dry mountains of Chile, the Vera Sea. Rubin Observatory is preparing for a mission of staggering scope. Its goal is to conduct a 10-year legacy survey of space and time, capturing a time-lapse movie of the entire southern sky. Night after night, its enormous mirror and giant camera will photograph the cosmos, cataloging billions of galaxies. The true power of this survey lies in weak gravitational lensing. By measuring the subtle, coherent distortions in the shapes of those billions of galaxies, Rubin will create the most detailed mass map of the universe ever made, a high-resolution chart of the dark matter cosmic web in our cosmic neighborhood. Meanwhile, on 2 continents, the square-kilometer array is rising from the deserts of South Africa and the plains of Australia. This is not a single telescope, but a vast network of radio antennas working in concert. Its mission is to listen to the faintest whispers from the early universe, tracing the distribution of neutral hydrogen gas during the cosmic dawn, the era when the first stars and galaxies flickered to life. By mapping how this primordial gas was structured and then ionized by starlight, the array will reveal how dark matter's gravitational pull guided the very first steps of cosmic structure. It will also use these vast maps to measure the expansion history of the universe with exquisite precision, placing tight new constraints on the nature of dark energy. Our view from the ground will be complemented by a new set of eyes in space. The European Space Agency's Euclid telescope is already on its mission, and NASA and Nancy Grace Roman Space Telescope will soon follow. Both are engineered as dark universe detectives. they will peer across immense cosmic distances using both weak lensing and a second technique called galaxy clustering. By measuring the three-dimensional positions of tens of millions of galaxies, they can track how the large-scale structure of the universe has grown over billions of years. Dark matter drives this growth while dark energy works against it. The precise rate of this growth over cosmic time is the most telling signature of the dark energy's strength and properties, revealing whether it is a simple cosmological constant or something dynamic and evolving. The hunt also continues closer to home in the realm of the ultra-small. Plans are already advancing for a future circular collider, a machine that would dwarf the Large Hadron Collider with a tunnel 100 kilometers long. The immense energies of such a machine could be the forge that finally creates dark matter particles, allowing us to study their properties directly in the debris of collisions. In deep underground laboratories, next-generation detectors with tons of liquid xenon or argon will wait in even deeper silence, their sensitivity pushed to the absolute limit, hoping to feel the faintest bump from a passing WIMP. These are not just bigger telescopes, they are specialized keys designed for specific locks. Together, they form an interconnected web of discovery, a global effort to interrogate the cosmos with a precision that was pure fantasy a generation ago. They promise to turn the theoretical maps drawn by our supercomputers and equations into a data-rich atlas of the unseen, transforming the greatest unknowns of our time into the foundational knowledge of the next. The ultimate hidden territory may not lie within our universe, but beyond it. This is the Multiverse Hypothesis, a staggering idea that our entire cosmos, with its specific laws and 4 visible dimensions, could be just one bubble in a frothing sea of realities. It is the logical, if speculative, extension of our most powerful theories. The concept of eternal inflation suggests that the Big Bang was not a unique event, but a single patch of space that underwent runaway expansion. In this picture, our entire observable universe is contained within one of these inflating bubbles, while countless other bubbles, each with their own separate Big Bang and potentially different laws of physics, continuously form in an eternally expanding meta-universe. String theory deepens this landscape. The specific way its extra dimensions curl up determines the physical constants of a universe, like the strength of gravity or the mass of an electron. The mathematics of string theory suggests not one unique solution, but an astronomical number of possible stable configurations, a vast landscape of possible universes. Our universe, then, might simply be one valley in this cosmic terrain where the constants are just right for stars, planets, and life to emerge. Scientists often categorize these ideas into different levels. A Level 1 multiverse is the simplest, arising from the implications of a perfectly flat and infinite cosmos. If space truly goes on forever, then every possible arrangement of matter must repeat. Somewhere beyond our cosmic horizon, there exists an identical copy of you reading an identical copy of this script, and an infinite number of variations where every possible choice branches into a parallel reality, all within the same continuous space. The Level 2 multiverse is the one of eternal inflation and the string theory landscape, where other bubbles have genuinely different fundamental laws. In some, gravity might be so strong that universes collapse instantly, or the weak nuclear force so feeble that atoms never form. Our universe is not special, just habitable. Then there is the Level 3 multiverse, which emerges not from cosmology but from quantum mechanics. The many worlds interpretation proposes that every quantum event with multiple possible outcomes does not randomly choose one. Instead, the entire universe splits, realizing every possible outcome in a new, branching timeline. In this view, the cosmos is a constantly fracturing tree of possibilities, where every decision, every random decay of an atom creates a new, equally real world. While these ideas are currently beyond the reach of direct experimental proof, they represent the final frontier of mapping the invisible. We have journeyed from hidden dimensions curled up at every point in space to the possibility of hidden universes existing beyond the ultimate veil of our cosmic horizon. If true, the act of mapping reality becomes an infinite task, a never-ending voyage through an archipelago of cosmic islands, each with its own unique and invisible architecture. Even the idea of a fundamental particle is a kind of illusion. To truly grasp the bedrock of reality, we must look beyond the tiny dots and into the fabric of space itself. This is the realm of quantum field theory, which proposes that the most fundamental ingredients of the universe are not particles but fields. Imagine all of space and time as a vast, still ocean. This ocean is not empty, it is filled with invisible, fluid-like substances, one for every type of particle. There is an electron field, a quark field, a photon field, all permeating every cubic centimeter of the cosmos, from the void between galaxies to the air in your lungs. What we call a particle is not a tiny ball, but a localized vibration in its respective field, like a wave rising from the calm surface of the ocean. An electron is simply a tiny, stable ripple in the everywhere present electron field. This perspective completely inverts our classical intuition. The universe is not a collection of separate things in empty space, but a vibrant, dynamic interplay of invisible fields. Space is not a passive stage, it is the active, humming performer. The most famous of these cosmic fields is the Higgs field. Unlike other fields, which are zero at their calmest state, the Higgs field has a constant, non-zero value throughout all of space. Think of it like an invisible cosmic molasses that fills the entire universe. As other particles, like quarks and electrons, move through this molasses like Higgs field, they interact with it. This interaction is what we experience as mass. A particle that interacts strongly with the Higgs field feels heavy, like wading through thick syrup, while a particle like a photon, which does not interact with it at all, remains massless and zips through at the speed of light. The discovery of the Higgs boson at the Large Hadron Collider was not the discovery of a particle that gives others mass, but something even more profound. The Higgs boson is the quantized vibration, the telltale wave, in the Higgs field itself. Its detection was our first direct proof that this invisible energy field is real, a monumental step in mapping a layer of reality that is always on everywhere. When we say we are mapping the invisible, we are no longer just searching for hidden objects. We are learning to chart the properties and interactions of these fundamental fields, the true, enduring substance of the cosmos from which particles briefly flash into and out of existence. Perhaps the most radical map of reality suggests the cosmos is not made of stuff at all, but of pure information. This idea, championed by physicist John Archibald Wheeler, turns our traditional understanding of physics on its head. Wheeler proposed his famous it-from-bit doctrine, a phrase that sounds simple but carries a universe of meaning. He suggested that every particle, every force field, every event in the physical world ultimately derives from binary responses to yes or no questions. At the foundation of existence, there are not tiny billiard balls but bits, the fundamental units of information. Think of the universe as an unimaginably vast and complex cosmic computer. What we perceive as an electron is not a tiny solid object, but a point in space that consistently returns a yes to the question, is there a negative charge here? The mass of a planet, the spin of a galaxy, the very fabric of space-time could all be emergent properties, a grand illusion generated by an underlying layer of informational transactions. This perspective finds a powerful echo in the holographic principle we encountered earlier. The mind-bending proposal that our three-dimensional universe is a projection from a two-dimensional boundary fits perfectly within an informational framework. The three-dimensional world we experience, with all its richness and solidity, is not the fundamental reality. It is the output, the display. The true reality is the vast, flat surface where the code is written, a cosmic hard drive storing the bits that define everything within the volume. Mapping the invisible dimensions of the cosmos then becomes a task of cryptography. We are no longer just searching for hidden particles or curled-up dimensions. We are trying to decode the universe's operating system. What is the programming language of space-time? What are the algorithms that translate simple binary choices into the complex laws of physics we observe? This is a truly profound shift in scientific paradigm. For centuries, the goal of physics was to understand the fundamental constituents of matter and the forces that act upon them. The periodic table, the atom, the quark, these were the milestones, but if the bit-from-bit idea is correct, then matter and energy are not the foundation. They are secondary phenomena, the user interface. The real work is happening in the code, in the informational relationships that weave together to generate the reality we perceive. This transforms our quest from mapping territory to reverse engineering the source code of existence itself. Your own brain is the ultimate mapmaker of reality. Every sight, sound, and texture you perceive is not a direct feed from the outside world, but a sophisticated simulation running inside your skull. Cognitive science reveals that your brain is a prediction engine, constantly taking the sparse, ambiguous data from your senses and weaving it into a coherent story. You do not see the light that hits your retina. You experience your brain's best guess about what that light probably represents, based on a lifetime of past experience. This means the solid, tangible world you navigate every day is a useful illusion, a high-resolution interface designed for survival, not an accurate depiction of objective reality. Think about optical illusions, where your brain confidently presents a perception that you know is mathematically false. This is not a glitch, it is a feature, revealing the brain's relentless drive to find patterns and create a stable, actionable model of the environment. Even the vivid sense of an unbroken present moment is a constructed narrative, with your brain editing out the tiny delay it takes to process sensory information, stitching together a seamless flow of consciousness from a series of disjointed signals. So if your personal reality is a curated simulation, how can you trust the scientific maps of dark matter or hidden dimensions, which are also models created by human brains? The crucial difference lies in the scientific method, a rigorous system designed to bypass our individual cognitive biases. A scientist's personal perception is untrustworthy, which is why every claim must be tested against shared, reproducible evidence. A gravitational lensing map is not accepted because one person sees a pattern in the data. It is validated because thousands of independent measurements, analyzed by different teams using different methods, all converge on the same invisible structure. The scientific map is not a single brain's guess, but a consensus model that has survived relentless attempts to prove it wrong. It is a reality check that transcends any one perspective, building a picture of the cosmos that is independent of our evolved intuitions and sensory limitations. This grand quest to map the invisible is not a solo mission for physicists alone. It demands a symphony of minds, a convergence of disciplines that each bring a unique lens to the darkness. Computer scientists are the cartographers of this new frontier, developing machine learning algorithms that can sift through petabytes of telescope data. These are not simple search programs, but neural networks trained to recognize subtle, complex patterns that would be invisible to a human eye scanning endless graphs. They can find the faint signature of a gravitational lens or identify the unusual light curve of a distant star that might be orbited by a dark matter object, revealing hidden structures in the noise. The hardware for this search is a triumph of engineering and materials science. To hear the whisper of a WIMP deep underground, the detector's components must be crafted from materials of incredible purity, metals refined to remove even the faintest traces of natural radioactivity that could mimic a dark matter signal. These are some of the cleanest, most silent environments ever created by human hands, a direct result of our most advanced understanding of molecular science. Even the philosophers of science play a vital role, standing at the edge of discovery to ask the foundational questions. What does it truly mean for something to be real if it is only ever detected through its gravitational influence? How do we validate a theory whose primary evidence is a mathematical elegance? They help clarify the assumptions woven into our models, ensuring our journey into the unseen is built on solid logical ground, not just elegant equations. This synthesis is our greatest strength. The artist's visualization makes the abstract tangible, the philosopher's critique refines the question, and the engineer's detector provides the raw, unassailable data. No single field holds the master key to the cosmos. It is only by combining these disparate ways of knowing that we can hope to triangulate the position of the invisible, building a map whose lines are drawn in the ink of shared human curiosity. The drive to map the invisible cosmos carries a profound ethical weight, a responsibility that grows with every new layer of reality we chart. This is not a purely abstract pursuit detached from human concerns. The very tools we invent to see the unseen often ripple through society in unexpected and transformative ways. The World Wide Web, for instance, was born at CERN, the European Particle Physics Lab, not as a goal in itself, but as a method for scientists around the globe to share data about the invisible quantum world. That tool for collaboration reshaped human civilization, altering how we communicate, learn, and connect. Similarly, the principles behind medical MRI machines, which allow doctors to peer non-invasively into the human body, are direct descendants of the nuclear magnetic resonance techniques developed to understand the fundamental spins of particles. The search for dark matter and hidden dimensions demands unprecedented technological innovation, pushing the limits of computing, materials science, and engineering. These advances inevitably spin off into the wider world, creating new industries and medical therapies long before the original cosmic mystery is solved. This power to generate world-changing technology comes with a dual responsibility for the scientific community. There is a duty to communicate findings with accuracy and humility, separating established fact from theoretical speculation in a landscape often clouded by hype and misunderstanding. And we must collectively ask who benefits from this knowledge. The immense cost of building a new particle collider or a space telescope represents a massive investment of public resources. This forces a vital conversation about the equitable distribution of scientific opportunity and its fruits. Should the quest to understand the universe's fundamental nature take priority over addressing pressing earthly problems? The answer is not simple, and the scientific enterprise must continually justify its value to the society that supports it. As we stand on the brink of potentially manipulating the fabric of space-time or decoding the universe as information, we are playing with forces whose full implications we cannot possibly foresee. The same fundamental physics that illuminates the birth of stars also unlock the power of the atom. This is not a reason to halt our exploration. but a compelling argument for weaving wisdom and ethical foresight into the very fabric of our curiosity. The ultimate challenge may not be mapping the invisible dimensions of space, but navigating the invisible dimensions of our own responsibility. This cosmic search is no longer confined to the experts. Every day, thousands of ordinary people are helping to map the invisible universe from their own homes, participating in a global movement known as citizen science. On platforms like Zooniverse, anyone with an internet connection can look at real telescope images and assist researchers in monumental tasks. You might be the first person to ever lay eyes on a distant galaxy warped by a dark matter halo, or help classify the shapes of millions of galaxies to trace the cosmic web. These are not simulations, they are genuine research projects where human intuition and pattern recognition, skills that computers still struggle to match, are put to work. A volunteer might spot a subtle, telltale arc that a machine learning algorithm overlooked, leading to the discovery of a crucial gravitational lens. This direct participation transforms the public from passive observers into active collaborators, sharing in the thrill of discovery and contributing tangible data to the frontiers of knowledge. This engagement hinges on the vital art of science communication. By translating the dense language of tensor calculus and quantum fields into clear narratives and vivid analogies, communicators build a bridge between the laboratory and the living room. They turn abstract concepts into stories of cosmic scaffolding and hidden dimensions, fostering a sense of shared wonder and collective ownership over these profound discoveries. Understanding that we live in a universe comprised mostly of invisible, mysterious components does more than just satisfy curiosity. It fundamentally shifts our perspective. Grasping the sheer scale of the dark cosmos and our tiny, illuminated niche within it can inspire a powerful planetary consciousness. When we see Earth as a fragile, visible speck set against a vast, dark backdrop, the artificial divisions that separate us seem to shrink. This cosmic context encourages a spirit of global cooperation, a recognition that we are all crew on a single, life-bearing vessel adrift in an immense and unseen sea. It deepens our appreciation for the thin, vibrant film of biology and atmosphere that we call home, the only part of this vast reality we can directly perceive with our senses. By opening the doors to this grand adventure, we ensure that the quest to map the invisible remains a deeply human endeavor, driven not just by a few, but by the collective curiosity of us all. A powerful idea must be more than just beautiful, it must be vulnerable. This is the bedrock of the scientific method, a process built not on faith, but on a relentless drive to prove our best ideas wrong. When we map the invisible from dark matter halos to curled-up dimensions, we are not writing a sacred text. We are drafting a blueprint that must withstand the storm of attempted falsification. A theory gains strength not when people believe it, but when it survives every conceivable experiment designed to tear it down. This self-correcting mechanism is our compass in the dark, ensuring that our maps, however strange, are steadily refined toward a more accurate picture of reality. Consider the case of dark matter, the prevailing model that an unseen particle provides the cosmic scaffolding has been incredibly successful, but it is not the only idea on the table. A compelling alternative exists called modified Newtonian dynamics, or MUND. This theory proposes that there is no missing matter at all. Instead, our understanding of gravity itself is incomplete, especially in the extremely weak gravitational fields found in the outskirts of galaxies. MUND suggests a slight tweak to Newton's laws, one that would explain why stars on the edges of galaxies orbit so quickly without needing any invisible glue. This is not a fringe concept, it is a serious, testable hypothesis, and that is the point. the scientific community does not ignore MUND. It actively pits its predictions against those of the dark matter model. Researchers run simulations, analyze galactic rotations, and study the cosmic microwave background, asking a simple question: which model's predictions better match the observational data? When the dark matter model correctly predicts the precise pattern of fluctuations in the ancient light of the Big Bang, and MUND struggles to do so without additional adjustments, the dark matter model is not proven right. It simply survives another round, its map looking a little more reliable. This process is the engine of discovery. Every null result from a deep underground detector, every failed search for a microscopic black hole, every observation that challenges a multiverse prediction is not a failure. It is a successful invalidation of a specific path, closing one door so we can focus our efforts on others. Our confidence grows not from certainty, but from the collective, rigorous effort to dismantle our own understanding, only to find that the most robust maps of the invisible still stand, waiting for the next great challenge. These threads of evidence now converge into a single, startling portrait of reality. The ghostly halos revealed by galactic rotations, the cosmic web charted through weak gravitational lensing, and the silent waiting of deep underground detectors all tell the same story. A universe we once thought was made of stars and gas is in fact built upon an invisible scaffold of dark matter. The accelerating expansion measured from distant supernova and encoded in the cosmic microwave background points to a second, even more dominant component, dark energy, woven into the vacuum of space itself. Our most ambitious attempts to describe this hidden reality, from the vibrating strings of string theory to the informational projection of the holographic principle, suggest that space has more dimensions than we can perceive, and that solidity itself may be a magnificent illusion. This is not a collection of separate mysteries, but different facets of a single, profound truth. The visible cosmos is just the glittering surface. Mapping the invisible is the work of connecting gravitational anomalies in galaxy clusters to the null, results in a liquid xenon tank, of tying the mathematical elegance of 10-dimensional geometry to the simulated evolution of a digital universe inside a supercomputer. It is a grand, collaborative program that links the physicist at the blackboard, the engineer tuning a radio telescope in the desert, and the volunteer at home classifying galaxy shapes online. This synthesized map, though filled with blank spaces and tentative borders, is our current best answer to an ancient question: what is the world truly made of? The answer is a cosmos where most of the substance and energy are forms we cannot see, a reality whose fundamental architecture exists in realms beyond our natural perception. This unified picture does not represent an end to the quest, but a new, more informed beginning, a foundation for the questions that will ultimately define our future in this vast and hidden cosmos.